Hello everyone, my name is Ivelin Georgiev and I want to show you some work we did in collaboration with Timo Schwandt and others on the impact of anisotropic photon emissions from sources during the epoch of reionization. But first, before even I can talk about that, I'd like to introduce the concept of the epoch of reionization so we're on the same page. The epoch of reionization is a second-order phase transition which occurs within the first billion years of the existence of the universe. And it captures a process where we start with a universe which is neutral, and there are no stars and galaxies, particularly rich in hydrogen, helium, and other light elements. And then, as matter coalesces following dark matter, creates the necessary halos for the first stars and galaxies to form. They themselves start emitting ionizing photons. You can sort of see this in cosmic dawn. My cursor doesn't seem to be visible. Where we go from this beige to pink color in the slice. The universe begins to ionize as ionized bubbles starts forming around the first galaxies. And these bubbles will grow the more ionizing photons escape, ionizing the neutral hydrogen around the intergalactic medium. And then depending on how the sources are clustered from the density field and their interactions, these bubbles will grow, overlap until eventually all of the medium in the outside of galaxies is completely reionized, and we sort of observe the universe that we observe today. This is quite interesting because it can tell us a lot about the properties of astrophysics in terms of this phase transition, but also we're capturing the effects that happens on cosmological scales and is affected hence by the properties of cosmology. What's also curious is that while telescopes such as the James Webb Space Telescope and Euclid observe galaxies at high redshift, there is another probe which is just as interesting, which is the 21 centimeter signal, which doesn't come from the galaxies but from the intergalactic medium itself. Because of the way hydrogen is coupled to its medium, it can emit a 21 centimeter photon, which traveling towards us redshifts and is detected in radio, but then depending on the era that we observe it, we can sort of get a tomographic picture of this. And because of the formation of these ionizing sources which remove the signal, we can sort of capture this sort of effect and see how it decreases, and by it learn not just about astrophysics but about cosmology. Yes, that's what I wanted to say. It contains properties of the ionization field and the density field. So how will we observe this actually? Well, there are plenty of radio telescopes at the moment actively searching and observing for the 21 centimeter signal during the epoch of reionization. And there's the SK, the Square Kilometre Array, the low component being built in Australia. You can see a picture here. And our first step in detecting the surface brightness temperature, the equation of which I've put on the side, is to measure the spherically averaged one-dimensional power spectrum. And of course, redshift is something you are all acquainted to, but you can see that thanks to every Z in my picture, you will also see the neutral fraction, 1 being for a neutral universe and 0 for an ionized one. And you can see the Fourier transform of the field, the ionization field, represented such that we have k-scales, low k-scales are large physical scales, and high k-scales, big numbers, or in this case are small scales. I'll just make the signal evolve. So this is a C2-ray simulation I ran. You can see that as we're going through the epoch of reionization, the power spectrum is changing. So it's capturing properties that are evolving differently on different scales. Capturing not just the evolution of the density field on low scales, but also the properties of the astrophysics in these mid or high K scales. So there's a lot of interesting information encoded into it, and hopefully a detection of this will help us discern between them. In my first paper, I studied a lot of different decompositions of the power spectrum. You can see here its formula. You can see the amplitude very much depends on properties such as omega b, omega m, and the redshift, among others. But what we noticed is that looking at specific bubbles and actually limiting the sizes of these ionized bubbles in our simulations, we can introduce a resonance feature which sort of acts as a smoking gun, sort of separating the cosmological part of the power spectrum, so the low K scales, from the astrophysical parts. And of course the feature itself being indicative of the typical size of these ionized bubbles. So in order to understand the low K scale, for example, we still must understand the bubbles themselves in order to reconstruct and understand what this amplitude and the shape of the features we observe. But the bubbles themselves are, well, just by referring to them as bubbles already implies a sort of assumption. So as a segue to the to the next slide, I wanted to talk about the assumption of isotropy. We have many different simulations that we try to model reionization. Often very small physical scales come with very high resolution because we can resolve a lot, but often we need to go above sample variance and have very large physical scales above hundreds of megaparsec, while simultaneously having exquisite resolution, but we'd often need kiloparsecs to model galaxies and all of their complex structures. This doesn't really happen that often or that well, so we often have to make some assumptions. And for large-scale simulations of reionization, this is often isotropic emission. So you can imagine this galaxy, which is ridiculously large maybe in this, but for show, would emit in every single direction equally, so sort of isotropic emission model, which is what we used. But in this paper, our motivation was to try to imprint a different feature, so assume a conical model, or if you prefer, a channel is emitted for a preferential line of sight of this ionized source, and you can see that it produces this conical shape with a semi-spherical hat, but I'll still call it a cone for simplicity. We wanted to see how we would implement this feature. We made it such that the amount of ionizing photons coming from that galaxy in this channel is the same, to sort of really capture how the geometry of reionization, or if you prefer, how the topology will change or the morphology, and then understand if this will impact some of our observables, such as the 21 centimeter signal. And there are hints that this is true in more high resolution but smaller physical scale papers that actually do observe that there are preferential channels. And often, in fact, the truth is somewhere in the middle. Of course, the structure of a galaxy, especially one at high redshift, is probably quite turbulent. There's different feedback processes. There might be many channels or fewer channels. They might be on and off for a certain period, linked to different properties of the galaxies. So the truth is often somewhere in the middle. I wanted to run this to show you an example of this anisotropy. So this is the Thiessen simulations, and they have very high resolution. I think this box is around 100 megaparsec, where the yellow now is the neutral field, so essentially a detection in the 21 centimeter signal. You see their power spectrum at the top right, and once I click play, the first stars in galaxies will start doing their work. So you can see they've started forming. Interesting things are happening. Things look more or less spherical, sure, but once you start examining, there's a lot of anisotropy. You see these features occurring. Maybe larger regions up there start producing very almost conical-like features. And of course, it's hard to tell because a single cell can be occupied by multiple galaxies, at least in our case. But it just shows that it's not necessarily just the typical spherical picture. So how do we want to test this? Well, we want to use a larger simulation of around 349 co-moving megaparsec and compare a model I had run before, assuming spherical emission. We'll call it the sphere model. And then we create 3 toy models which are with conical shapes. One of them is static, so the cone will not change location. We call this cone 1, and it has an angle of around 30 degrees, while cone 3 is the exact same model, but the position of this channel changes randomly over time. So we wanted to see if this causes an effect. While cone 2 is more wider, so it's around 60 degrees. So we wanted to see how the size of the cone affects this as well. In the paper, of course, we're going to compare a lot about the morphology and topology of these regions, but I will focus on just a few specific parts of the paper. So what you can see here, the ionization slices of the reionization simulations for the different cases compared to the fixed ionization fractions. So yellow means ionized, blue or slash violet or slash indigo is neutral, and they are compared to the same neutral fraction. So let's say the amount of yellow in the box is the same when you compare them. So the redshifts do have a slight difference, but there's a lot of information here. So I'll just pick a region of interest, maybe this sort of not the biggest ionized cluster in the simulation, but still an ionized cluster nevertheless, and give an example of what you can see and infer from this. So I also chose this because I thought it was funny. For me, I would call this a great example of the assumption of a spherical cow, or in this case, a spherical bunny, or whatever fictional animal you would like to name this. But you can see some interesting features, so I'm going to use this bunny example. So for example, just like we saw in the Thiessen simulations, removing this isotropic assumption, you can see that our bunny actually has ears. So the cone is working. This is the narrow cone case. You can see anisotropic emission at the top, but then on the other side, by sort of bunching up our channels, there are regions inside this ionized cluster, such as the nose or mouth of the bunny, which are somewhat neutral. So the cones, no cones have met in this area and ionized this. But on the other hand, you can see what I've sort of made as a tail. Just as the cones themselves have not interacted, in some case you could say they've conspired together and created a longer ionized feature. And still, at the end of the day, because we compared similar neutral fraction, you can see a sort of peppering additional ionization sort of scattered in more separated regions in the anisotropic model than the isotropic model of the sphere case. And this, of course, changes how, depending on which type of model that we looked, our weird little bunny was very pronounced for the cone 1 case, but then increasing the width of the cone, you can see in the cone 2 case, the ears are sort of melted. It doesn't look as pronounced anymore. But we're taking the cone 1 case and just varying it, produces a very similar spherical feature to the one we observed in the sphere. Regardless of that, you can still see this sort of peppering structure, or this small scale power for the conical cases, which decreases from cone 1 to cone 2 to cone 3 respectively. So we wanted to see, since this is affecting the ionization field, how is it going to affect the 21 centimeter power spectrum, and what does it have to do with our observations? So here I compared 3 panels of the 21 centimeter power spectrum, 3 different global neutral fractions, 0.3, 0.5, and 0.7, where the grain bands are noise for a potential observation with SKA, with sample variance included, but assuming 1000 hours, so I guess quite optimistic. Nevertheless, interesting things are happening. So maybe I'll start at the high K scale, so where the gray band is most visible, about above 10 to the naught, so 1. This corresponds to the smallest physical scale, so that peppering before is more visibly imprinted now for you to see. There's more power in the conical cases than the spherical case. And this is usually an interesting area of research in 21 centimeter science, because you are sort of sensitive to the coupling of ionization on very small scales and matter. So it is, people have said that maybe you could use it to discern different dark matter models, but you can see that by making the channel assumption or the conical assumption, it changes how the fields are correlated on those scales, so one must be careful. Regardless of this, given our resolution, we are sensitive to aliasing here, and in the end of the day, the noise is quite large, at least for this observation. So we can't be too conclusive on this. Moving on the opposite side of the figures towards the low K regime, so below 10 to the minus 1, which are the largest physical scales, we see differences again, but within the region of sample variance, where there's a difference in the ratio, which I've plotted below for simplicity. There is, I think, exactly less power for the conical case, but later there is more power as reionization progresses. So this is maybe, in a sense, what the tail of our bunny example is showing. regions can connect and more large-scale power is visible on those scales. So this would affect our inferences drawn from the low K21 centimeter power spectrum, or if you prefer, the large-scale features, but it's still within sample variance. But it is interesting. Lastly, I wanted to center on the middle point, where the differences are more stark and the noise is the smallest, because this is the interesting range for telescopes such as SKA, LOFAR, Hera, MWA, etc. And you can see now we are outside of the noise regime, and this is more clearly visible. And this happens to be around the part where the sizes of the bubbles appear in the power spectrum, offering us an ability to observe and discern between them. Of course, the more wider the cone gets, or the more it varies, the difference becomes less pronounced, but it is there. And this is an interesting first foray into this study. And of course, a good understanding of this can still allow us to understand about the large-scale structure. One just has to have a good understanding of how this changes. Also note the difference in power on different K scales. We can talk about this later. I'm probably running out of time, so I just want to say my last two slides. We also look at the anisotropy, if there's any anisotropy introduced in the power spectrum by giving a preferential direction. So we study an anisotropy ratio over a power spectrum and find that there is not that much of a difference. And this happens because I've put this little picture here of a more complex cone with it being averaged out with a spherical kernel. Exactly what we discussed before, having the different cones sort of smooths out this information. But the difference in K scale was visible in the power spectrum itself, because you can see our little smoothed bubble does differ as you go out from the center. The fluctuations are changing. Okay, so I wanted to show my conclusions now. In short, let me just load them. We examined 3 different simulations of the epoch of reionization of around 350 comoving megaparsec to test the assumption of anisotropic emission. And we find that it does impact both small and large scales alike, and it is potentially observable. This is some of the first tests of this, and it offers us a good insight about how the power spectrum will change given different emission channels, and then how one should be careful with our inferences, or what we can deduce from the power spectrum studying the large K scales. Okay, I believe my time is almost up. I'm happy to talk to you more about this. Bye bye.